Hello and welcome to another episode of Earth911's Sustainability in Your Ear. I'm Mitch Ratcliffe, and we are back to have another conversation with an innovator in the sustainability space. You know, folks, so much of what we buy today is shipped halfway around the world. Sometimes the components of a product are shipped from the United States to Asia, processed, and then shipped back. Almost all of that shipping activity burns oil today, which accounts for about 2.5% of the annual carbon footprint of human society, according to the European Commission's Climate Action Office. So we need to change the fuels used to power seagoing freight vessels to sustainable alternatives, and several are emerging. One of those is ammonia. It's not just for cleaning and fertilizer anymore. Our guest today, Stephen Crolius, is the co-founder and president of Carbon Neutral Consulting, a New York-based sustainable business consultancy. Stephen previously served with the Clinton Foundation's Climate Initiative and has been the president of the Ammonia Energy Association. He and his team recently released a report, the Ammonia Report, which is an analysis of the prospects for using ammonia as a maritime fuel instead of the heavy fuel oil, that petroleum-derived traditional source of maritime energy. Ammonia has been used in fertilizer since the early 20th century, a development made possible by the emergence of the Haber-Bosch process for mass producing the chemical. And that actually is one of the greatest industrial innovations in history. It changed farming completely. Now ammonia is coming into use as a fuel or an intermediate medium for storing energy, and it can be processed to yield pure hydrogen in fuel applications. After reading the Ammonia Report, we wanted to learn and ask about the implications for the transition to a post-carbon economy. You can learn more about carbon neutral consulting at carbonneutralconsulting, all one word, carbonneutralconsulting.com. Welcome to the show, Steve. How are you today?
Well, I'm doing very well, Mitch, and thank you very much for having me.
Well, it was an interesting report, and I wanted to both introduce people to the topic and get into some of the details. A lot of people wouldn't think of ammonia as a potential fuel. How can you use it? Is it primarily in fuel cells, which rely on a chemical reaction, or can it be burned? And what are the byproducts of that combustion?
Well, it can be used in essentially every type of energy extraction process that we currently use with petroleum-derived fuel. So it can be used as an internal combustion fuel in both gasoline or auto cycle type applications, like for cars, or diesel cycle. If you're going diesel cycle, you need to have a pilot fuel, but that's probably a layer of detail that we don't want to get into at this time, but it's certainly possible. It can be used in combustion turbines. It can be used in industrial processes that require heat. Closely related to that is it can be burned in a boiler, such as is used to generate electricity. And as you indicated, it is very well adapted as a fuel for fuel cells, both the low temperature membrane type fuel cells, like along the lines of the fuel cells that are in that are in vehicles today, and also in high temperature type fuel cells that actually are probably have the highest energy conversion efficiencies of any of these types of conversion devices.
Now, go ahead.
So you had asked about byproducts of combustion. So ammonia, most people are aware, is a very simple molecule consisting of one atom of nitrogen and three atoms of hydrogen, which means when you burn it, what you get from the process is nitrogen, which nitrogen turned back into the inert form that's in the atmosphere. In fact, it's 78% of the atmosphere, so it just goes back to being atmospheric nitrogen. And the hydrogen gets combined with oxygen to make water. So very simple, straightforward result from combustion.
Well, let me ask about the nitrogen. When you burn ammonia, does it produce nitrous oxide, or is that an interim state of the molecule before it becomes nitrogen, atmospheric nitrogen?
Um, I to say that it produces no nitrous oxide,
Hmm.
I'm sure is incorrect. I'm sure in the combustion process,
Right.
at least as a combustion intermediate, I'm sure there's a little bit of nitrous oxygen. Uh, um, but the, uh, the main issues from
Hmm.
burning ammonia, things you don't want, undesirable byproducts are uh, nitrogen oxide, not nitrous, but nitrogen oxides,
Okay.
NOx, and unburned ammonia, referred to as ammonia slip. And these are undesirable. These are pollutants,
Hmm. Yeah, they're
and
carbon equivalents that have a large impact, 298 times more atmospheric warming potential per pound than CO2.
nitrous, yes. I'm not sure about the global warming potential of nitrate,
Okay.
but nitrate NOx is absolutely is a contributor to in enough quantity well, in any quantity it will tend to um, reduce the pH of water in the atmosphere,
Hmm.
creating rain tending toward acid characteristic. So these are undesirable pollutants that must be, and fortunately can be, controlled through normal pollution control measures.
Okay.
Interesting point is that ammonia is used as a selective catalytic reagent, reduction reagent, for example, in power plants that burn coal. So their tendency to produce NOx is controlled through
Hmm.
flue technology applied to the flue gas, and ammonia is injected into the flue gas in order to react with the NOx and drive it below targeted levels. So in fact, you have if you're burning ammonia and you have NOx on the one hand and unburned ammonia on the other hand, it's a relatively straightforward process to create the environment in which those two species can react with each other and push the reaction products overwhelmingly over to just pure nitrogen and water.
So it sounds like with that kind of a scrubbing technology already in existence, that these systems could be tuned to clean themselves to some extent. Even the fuel filtering the emissions before it's burned as fuel. That's really interesting. Now, the question I have about the ability to offset the 2.5% of global emissions currently related to maritime shipping is this. Right now, making ammonia accounts for about 1.8% of global CO2 emissions. And that's according to the Royal Society of Britain. Does the prospect of scaling up ammonia production to offset oil burning actually potentially lead us to more CO2 associated with shipping than before?
Yes, that would certainly be the case if the plan was to scale up conventional ammonia production as
Okay.
to provide a fuel for anything, including the maritime sector. But that's not in the cards. That's in fact not what's happening. In fact, there have been very few, if any, conventional ammonia production plants announced since, let's say, 2018. I don't want to say no plants,
Okay.
but very few. And instead, there's a massive effort to scale up production of ammonia that will have a low carbon footprint.
Okay.
And so the people, I'm sure, have heard the colors referred to hydrogen, blue hydrogen, green hydrogen. Same applies to ammonia, blue, green, and blue means it's the feedstock is natural gas.
Mm-hmm.
And so what happens with blue is blue hydrogen is the carbon from the natural gas is captured, and then we all hope and expect that something appropriate would be done with that captured carbon, whether it's sequestered in a geological formation or otherwise. So that's blue hydrogen.
Mm-hmm.
Once you have blue hydrogen, you can feed it into the ammonia, the normal ammonia production process. You make some, actually quite a few simplifications on the front end of the process.
Mm-hmm.
But then you can produce blue ammonia. And then, of course, on the green side, green is normally used to mean that the source of the hydrogen is electrolysis of water. And if you use renewably generated electricity to power the electrolysis of water, then you wind up with green hydrogen, and then that can be turned into green ammonia.
So what's the prospect for growth in the green ammonia production industry at this point? Do you see investment flowing into that? Or as you said, since 2018, a lot of things have simply been on hold. Are we waiting for a revolution in ammonia production?
No, it's really an incredible story. I mean, just it kind of takes the breath away. A number of companies have appeared, and they've got the capital and the backing, and they've done their investigation of potential sites,
mm-hmm.
and they are have announced a large amount of new capacity to produce, reduced low carbon hydrogen and ammonia. This is happening in a number of places around the world, and we're talking about, they usually use a electricity power capacity to describe how big their efforts are.
Okay.
And so if you take a very large power plant, sort of the largest power plants that are out there, that have been out there in current society, that's about a gigawatt. A very large power plant would produce about a gigawatt of electricity. So the projects that have been announced by a number of players on the green hydrogen and green ammonia side are in the tens, the dozens of gigawatts.
Okay.
One company has announced an aspiration to get into the hundreds of gigawatts. And at the Ammonia Energy Association, we did a little back of the envelope exercise and discovered that that this one company with their plans and their hundreds of gigawatts, that would be about the same amount of energy produced each year by this company as is produced by Chevron, the oil company, the U.S. oil company.
So what percentage of maritime shipping oil, bunker oil, could be replaced with that capacity at this point? Where are we in terms of beginning and moving through the migration from oil to ammonia for shipping?
Well, to replace all of the petroleum-based maritime fuel used today,
mm-hmm.
that would take something like 5 times the amount of ammonia. So we have to multiply the ammonia production capacity by a factor of 5.
Okay.
Just to meet that demand. So that sounds like a heavy lift, and it is a heavy lift. But this will play out over the next 20, 30, maybe 80 years. If you look at what the International Maritime Organization is saying about its path for sectoral decarbonization, they want to have that what they've floated is a 50% absolute reduction in greenhouse gas emissions from the sector, a 50% reduction by 2050. So if we have 28 years to ramp up the low carbon ammonia capacity to meet the need for 50% of the sector's fuel needs, that's a very doable thing. And the 28 years that's an important amount of time.
Yeah, just the replacement cycles in that time frame could result in a lot of improvement.
Precisely, you just nailed it.
Well, now, so do you see petrochemical companies shifting from processing oil to manufacturing green hydrogen? Is that one of the potential catalysts of a more rapid transition?
Yes, yeah, it's absolutely happening. I can tell you that you mentioned the Ammonia Energy Association in your introduction. I can tell you that a number of oil majors are members of the Ammonia Energy Association and have been for several years already. I don't want to start mentioning names because I'm afraid I'll leave someone out, but folks who are interested can go to ammoniaenergy.org, and there's a page there that lists the association's members, and you can scan down. There's about 130 odd members today, and you can scan down and see all the companies that have joined.
Now, let's talk a little more about ammonia as both a fuel and a medium for energy storage. Ammonia can be cracked, the molecules separated to create hydrogen, pure hydrogen, which is another clean fuel. How do the economics of just burning ammonia compare to that of using ammonia to make fuel-grade hydrogen and then burning it? Is that a necessary step for a cleaner economy, or is it essentially a wash?
No, this is a very consequential topic. What I anticipate is that the benefits, the economic benefits of using ammonia directly as a fuel will be so pronounced that the pre-use cracking, as you described it, won't make a lot of sense in the overwhelming majority of cases. The one case where it seems like this could become a practice is light duty transportation. So you got fuel cell cars. They've got their proton exchange membrane fuel cells that need a very, very, very pure hydrogen, and delivered to them at fueling stations all over the countryside. And the question of how, if that's the mission you've committed yourself to make hydrogen, a very, very pure hydrogen, available in tens of thousands of locations across, let's just take the United States, across the US.
Sure.
Then you have a question about what is going to be most economical. And indeed, in that case, it's unlikely that moving gaseous hydrogen around is going to be a dominant mode,
right?
Because moving gaseous hydrogen around is very expensive, because if it's gaseous, it's there's only so much in a tank on a truck. If you liquefy hydrogen to move more of it around, now you have just added so much cost that you're now better off having turned the hydrogen into ammonia and moving the ammonia around. And so, indeed, it's very possible that ammonia would become a preferred, call it a chemical storage medium for hydrogen, that could then be delivered to hydrogen fueling stations. And the technology, there's a lot of companies working on technology to do the cracking and generate this very high purity hydrogen.
So you could literally move ammonia to the station, crack the ammonia there, and deliver hydrogen to the vehicle.
Exactly. As I just mentioned, I mean, there's a lot of companies that are betting on that's going to be an important market or application for their technology. People may say, it looks like in light duty transportation that battery electric is running away with the race. So we'll see how that develops. In other other applications, it is likely going to be much more economical to just use the ammonia directly as a fuel. You don't, in many applications, you can use it just straight up as ammonia. Some applications, it is beneficial to do a small reforming step before the fuel is actually burned. When I say a small reforming step, if you put ammonia at a moderate temperature, a few hundred degrees Celsius, 2, 3, 400 degrees Celsius,
Mm-hmm.
over a catalyst, it will spontaneously decompose into, some part of it will decompose into hydrogen. And that mixture of hydrogen and ammonia, actually, if you get the proportions just right, it burns in a manner that's kind of indistinguishable from the way natural gas burns. And the key thing is, if you're burning it in a heat producing reaction, which kind of by definition you are, then you have a lot of heat you can apply to heat up that reforming step, and the catalyst is just there anyway. So you just have your ammonia flowing through this heated chamber over the catalyst. Some of it breaks down to produce hydrogen. You just put that into your combustion process, and you're good to go. But a lot of applications, like, for example, not limited to, but including the fuel cells, you can just take straight ammonia and put it right into the fuel cell. And you're probably, in a lot of cases, you're better off in that situation than you are with a hydrocarbon type fuel.
So we'd be moving ammonia around as a fuel or as a store for energy that could be then turned into fuel. But that's a lot of ammonia moving around. Fossil fuels have this terrible secondary environmental impact, which is just the pollution caused when it's spilled in water or in soil. How does ammonia compare as a safe material, if in fact it is safe, when accidentally released into the environment? What do we face another generation of chemical spills, for lack of a better way of describing it, that we need to be planning to take care of or reduce the incidence of?
Yes, this is a critical topic. There's a few different ways to come at it. One way, the first way to come at it is to say ammonia is a hazardous chemical, hands down. There's no other way to describe it. It's a hazardous chemical. If it contacts, flesh of a living organism, you could say it burns it, or it degrades it. It causes chemical degradation, and so it needs to be handled as a hazardous material and with consummate respect. Now, another thing that can be said here is that, as you pointed out in your introduction, we have been making ammonia and shipping ammonia all around and using ammonia in very large quantities for more than 100 years. And in that time, we've learned an awful lot about how to handle ammonia safely. So your question about how does ammonia's hazard profile compare with that of, let's say, a transportation fuel, a petroleum-based transportation gasoline. The profiles are different, but the degree that the risk can be managed is about the same, so that we're not going to be causing any higher degree of harm if we switch to ammonia than we're currently experiencing with petroleum-based fuels. The third way to come at this is to understand that ammonia is a constituent, a naturally occurring constituent of the biosphere. Everybody's aware that we produce ammonia within our bodies, excrete it. and that ammonia that we excrete, goes into the water bodies or into the soil or whatever. It gets actually taken up by plants and turned into other things. When the plants die, turned into the molecules of life. When the plants die, they go back into the soil, and microorganisms decompose the nitrogen, turn it back into ammonia. So ammonia is part of that natural cycle, which means that if there is a spill into a water body or onto the land, there will be serious harm done in immediate proximity to the spill. It essentially will kill everything but key thing, in a discrete, confined area. Once it has reacted chemically with something, it's now harmless. It doesn't exist anymore as ammonia. It's turned into something else.
So that's very different than an oil spill, for instance, which would just perpetually be there.
Exactly.
You're saying that essentially nature has the ability to clean up ammonia spills more efficiently than the way we would with oil.
Yeah, so we're in a situation where two things are true at the same time, two things that seem maybe a little bit at odds, but they're both true, which is A, it can cause a lot of harm, but B, it's part of a natural cycle, and that because of that circumstance, the harm it causes will be short-lived and limited in scope.
Okay, well, I'm sure that our listeners are going to want to look into that some more. So we'll try to provide a couple of links in our introduction. Let me ask this: are there other industries that are considering ammonia besides maritime shipping as a fuel? And do you see either a lot of contention between industries to get available supply, which would drive up prices, or that bit much larger a set of investments to create more capacity? Where are we going, and what other industries might we expect to see ammonia start to power?
Yeah, well, it's a very interesting time right now, because I mentioned the companies that are building capacity to produce low carbon ammonia in what will be millions of tons, and we've talked about maritime as one industry that is likely to use that ammonia, but there isn't, to my awareness, there aren't yet any supply contracts in place. We're just a little bit early for that.
Okay.
And where else ammonia will go, it's even less clear beyond maritime how it will play out. But there's a couple of things that are in view. One is the East Asian countries, Japan, South Korea, China, who are net importers of energy, and especially South Korea and Japan. And Japan has been a real leader. I would say Japan has been the global leader in thinking through a hydrogen-based economy, and that means Japan did a lot of work to assess the various ways that a hydrogen economy could be implemented, and they haven't officially anointed ammonia as the way to go over other options, but ammonia is inarguably receiving the greatest amount of investment now, ammonia-related systems in Japan, and doing so many things there, many related to the power sector. One of the things they're doing in the power sector, and this is maybe even a nearer term opportunity for low carbon ammonia. This is what they're doing or what they're planning to do is co-firing their coal-fired plants, co-firing with ammonia. And people will say, wait a minute.
Is a transition strategy?
As a transition strategy, exactly.
Okay.
That's the wait a minute. Like, what sense does that make? Doesn't this perpetuate the life of the coal plants? But what's happening is the Japanese started with a couple of percent, and 5 years ago, 4 years ago, now they're up to 20%, and they have announced plans to get up to 50%. In the meantime, we just had an announcement out of China that kind of caught everyone by surprise because we didn't see it coming. China is doing now 35% co-fire, and these percentages are as a percent of the total energy that's consumed. So it's not by mass; it's by joules. So Japan has a explicitly articulated program for developing hydrogen, and that means ammonia uptake over the balance of this decade and then beyond. And they're talking about, if I'm remembering off the top of my head, I think they're talking about 1 million tons consumption in 2030 for Japan itself. And then Japan is a supplier of has been a supplier of coal-based generating technology to other Asian countries. And now Japan is anticipating that it will be able to bring a number of those countries along with them. So, we're looking at by 2050 on this track, tens of millions of tons of ammonia that could go toward reducing the carbon footprint of electricity generation in Asia.
Well, you said a mouthful a moment ago when you said we live in interesting times, because it certainly is a transitional moment, and it's fascinating to hear about particularly Japan's investment. This is going to change the geopolitics of energy pretty substantially. But this is not a resource that you have to fight over, like, for instance, a seam of coal in the ground. Ammonia can be made from stuff in the air using the Haber-Bosch process. It's fascinating. It changes not only the dynamics, but the way that the battle for supremacy will happen. And there's a lot to unpack there. How can our listeners learn more and follow along with the development of ammonia as a fuel?
Well, I mentioned the Ammonia Energy Association a few minutes ago, and the Ammonia Energy Association produces a weekly newsletter called Ammonia. It's just called Ammonia Energy, and it's free. And anybody who's interested, as I mentioned, can go to ammoniaenergy.org, and it's easy to find the newsletter. Click on articles. That will bring you over to where all the articles are presented, and then you can sign up for the free newsletter, and it's pretty extraordinary. The scope of what is going on in the newsletter, we try hard to keep up with it, and lately there's been a real challenge. There's so much going on.
Well, that's good to hear. And Steve, I want to thank you for taking the time to share the story about ammonia as energy. Come back and tell us how it continues to develop.
Yeah, I would welcome the chance to do that. And thank you again for having me.
We've been talking with Steve Crolius. He's the co-founder and president of Carbon Neutral Consulting. And you can find out more about Carbon Neutral Consulting at carbonneutralconsulting, all one word.com. Folks, the transition from one form of energy to another is going to be bigger in terms of its economic and social impact than the transition from analog information to digital information. I've been covering that transition for years. And in this case, we're talking about changing virtually everything from the ground up in our economy. And it is going to be a fascinating and very opportunity-rich time as we make this transition. But if we don't make this transition, folks, we are absolutely going to have a crisis, and it is time to take that seriously and make these investments. So when you're shopping, think about whether or not the product that you're buying is being shipped around the world, and then start asking questions of the people who you purchase from about how they move their product back and forth between the source of materials, manufacturing, and you, the person who ultimately uses and has to take care of it at the end of life. So this is a big change, and I hope that this podcast and all the others that we do are helpful to you. This is Earth911's Sustainability in Your Ear. I'm Mitch Ratcliffe, and we're going to be back soon with another innovator interview. But in the meantime, folks, I hope you'll take care of yourself, take care of one another, and all of us take care of this beautiful planet of ours. Have a green day.